about. So to start with, we'll work over a field of complex number. I will denote it by F. I guess sometimes C, but in general F. A vector space is a Lie algebra if it has a multiplication which we call bracket, satisfying certain conditions. In particular, the bracket is bilinear and it is alternating and it satisfies the so-called Jacobi identity. A typical example of a Lie algebra is, of course, the set of all n by n matrices with the commutator product, namely AB minus BA. When we multiply two matrices, we look at AB minus BA. Well, the n by n trace zero matrices are of more interest to us because that actually forms a simple Lie algebra because it does not have any proper ideals. So I will just to motivate, I will take the 3 by 3 trace zero matrices and the bracket operation, as I said, or the multiplication is AB minus BA. And as you know, the basis for this Lie algebra is two diagonal elements, which I will denote H1 and H2, and the off diagonal and matrix units E12, E21, E23, E32, and E13 and E31. This is a 8-dimensional Lie algebra. And the subalgebra, abelian subalgebra spanned by H1 and H2 is what we call the Catan subalgebra. In particular, you can easily check that the bracket or multiplication of H1 E1 is 2E1, H2 E1 is negative E1, and H1 E2 is negative E2, H2 E2 is 2E2. Well, this is important because I want to introduce the concepts of determining this affine Lie algebra starting from a affine matrix. So let us take the linear functionals on H, epsilon 1, 2, and 3 to be projection to the corresponding diagonal entry. And then we define alpha 1 to be epsilon 1 minus epsilon 2, alpha 2 to be epsilon 2 minus epsilon 3, and lambda 1 to be epsilon 1, lambda 2 to be epsilon 1 plus epsilon 2. These alpha 1, alpha 2 are called simple roots, lambda 1, lambda 2 are called fundamental weights. And if you notice, just to work out these linear functionals, you will see that alpha j hi, I will denote it by aij, is 2 when I is equal to j and negative 1 when I is not equal to j. So associated with this simple Lie algebra SL3, we have this matrix 2, negative 1, negative 1, 2, which we call the Catan matrix. And indeed, we can construct this Lie algebra via generators and relations starting from this 2 by 2 Catan matrix. And that's the important part of it. As far as the notation, we will denote this capital Pi to be the set of simple roots, pi check to be the set of simple co-roots, and capital P to be the weight lattice. So it is an integral lattice spanned by lambda 1 and lambda 2, and the co-weight lattice is spanned by H1 and H2. And this set, the Catan matrix, pi, pi check, P check, and P is what is called the Catan datum. So starting from this Cartan data, we can construct the entire Lie algebra. That's the whole point. Via generators and relations. Now let's talk about representation. That will be critical for us. A vector space is a G module if there is a map from G cross V to V satisfying these three relations. Oh, sorry, I have an extra bracket here. It should be, should not be there. But anyway, the first two relations, as you can see, that kind of shows the linearity in the X and V coordinate. And the last one is basically the compatibility of this action of G on V with respect to the multiplication in the Lie algebra. And when we have a G module, we say that V is a representation space for the Lie algebra. In particular, any vector in the Lie algebra can be represented as a linear operator on V. Okay. Now, in this particular example, let's take the Lie algebra SL3 and let's take the three-dimensional vector space F of column vectors F3 and take V1 to be 1, 0, 0. Then you see that if I so here the action is just matrix multiplication. Here you have X is a 2 by 2 matrix and V is a column vector. So it will produce a column vector. So if we multiply E12 by V1, you will get 0. If we multiply E23 by V1, we also get 0. And that makes it a maximal weight vector. And also we see that H1 V1 is just V1. H2 V2 is 0. So this means that the weight of the vector V1 is capital lambda 1, the fundamental weight. And as we see, this weight vector V1 generates the entire vector space because F1 V1 is V2 and F2 V2 is V3. So this particular module is called a highest weight module with highest weight lambda 1. And of course, this is just a baby example, but we will keep this one in mind. Another typical example of module is the so-called adjoint action of a Lie algebra on itself. Because if we take any two vectors X and Y, of course, we can let X act on Y by multiplication in Lie algebra. So bracket XY produces a vector in G, and this action is called adjoint action. So if we take G to be SL3 and take V to be G itself, then under adjoint action, V is a G module. And if we write down the action of E1, E2 on E13, we see it's 0. So in this particular case, E13 is a highest weight. And if we let H1 act on E13, we see we get E13. And H2 on E13 is also E13. So it's a 1. That means that the highest weight E13 has weight lambda 1 plus lambda 2. And indeed, by letting the rest of the generators, F1, F2, act on E13, we can produce all the other basis vectors. So this is again, the adjoint representation is a irreducible representation And it is a highest weight representation with highest weight lambda 1 and lambda 2. We'll keep this one in mind for later use. Now, motivated by this idea that we can produce any semi-simple Lie algebra from a integral matrix satisfying certain properties, two bright graduate students, Victor Katz and Robert Moody, working at different places, decided to take it to the next level. Look at any integral matrix satisfying the similar property, but took out the positive definiteness, which is satisfied by a Cartan matrix. And then the Lie algebra that it generates via generators and relations, that's what is called a Casimudi Lie algebra. In particular, if the Cartan matrix satisfies these are the typical conditions that you already saw. And the additional condition here is that it has a null vector, meaning that it's the null space of this matrix is one-dimensional, and there exists a non-zero vector x. Of course, this can be uniquely determined if I require the entries to be integers, and the GCD of these integers is 1. Then this is uniquely determined. And that's what I denote by A0, A1 up to AN. So that AX is 0. So it's the corank of a affine Cartan matrix is 1. It is a symmetrizable matrix in the sense that there exists a non-singular diagonal matrix D such that dA is symmetric. And if A is a affine, I wrote GCM here, I am just referring as a affine Cartan matrix. So if it is a affine Cartan matrix, the transpose is also a affine Cartan matrix. And from these conditions of the defining properties, the affine Cartan matrices are completely classified. Not very difficult to do that. And corresponding to each type of affine Cartan matrix, we have a corresponding affine Lie algebra generated via generators and relations. And that's what we call the affine Lie algebra, and that will be my focus today. Okay, so here are some examples. For example, A11 is this smallest affine Cartan matrix. A21 is a 3 by 3 case. Observe that if I delete the first row and first column, what you see here is the Cartan matrix for a cell 3. And that's A2. Okay? And there is a important observation here that actually we can start from this simple Lie algebra cell 3 and construct this affine Lie algebra explicitly by looking at polynomial maps from a cell 3 to a unit circle and taking a central extension of that. Okay, and G2 upper 1, this is this matrix. Observe the entries here are not just -1, but this is -3. And that indicates the root lengths are unequal. Okay. And G2 is something called a special simple Lie algebra. Okay. Now, of course, A11 and A21 are already symmetric, but observe that G21 is not symmetric, but if we take the diagonal matrix to be 1, 1, 1/3, it is symmetric. D times this matrix is symmetric. Okay, so any Cartan matrix is symmetrizable. Now, for a affine Cartan matrix, we define dual weight lattice to be the pre-abelian group generated by H0, H1 up to Hn. Now, because the Cartan matrix has co-rank 1, it has nullity, we have to extend this to be to include one more length for technical reasons. And that I denote the basis to be D. So in particular, this dual weight lattice has rank n plus 2. Oh, incidentally, for the affine, we always start from 0 as opposed to 1. Part of the reason being that if you drop the 0, as I showed you, then you will get a simple Lie algebra or a positive definite Cartan matrix. And then you just take the corresponding vector space with spanned by P check. That's the Cartan subalgebra of the Lie algebra. And we define the linear functionals alpha I and capital lambda I on H, just as I told you before. Alpha j hi is aij. But now I have to tell you what alpha I does to D, that extra dimension. And we define it to be delta I0. Okay, so it is 0 unless I is 0. Okay, this actually is because the Cartan matrix is singular. So in order to force linear independence among the simple roots, we have to do this. That is the technical reason. And we define lambda I as lambda I on Hj is delta Ij. On D, we will take it as 0. You can take it non-zero also, but I will take it 0. That's just a scaling number. There are situations where you want to take it as non-zero, but for my purpose, 0 is good enough. So, and this again, the alpha i's are simple roots, and now we have what I have shown you is I have the Cartan datum A, phi, phi check, P check, and P for this affine Lie algebra. And with this data, we can actually construct the entire Lie algebra. And indeed, the Lie algebra is generated by H and the EIFIs, satisfying some relations. And among them, as I showed you for the SL3 case, of course, these 4 relations called the Cheveley relations will always hold. And there are some more. Okay. Now, if we fix the index I to be any number between 0 and n, then the span of hi, ei, and fi is a simple Lie algebra, finite dimensional simple Lie algebra, the smallest one, SL2. 2 by 2 matrices of trace 0. That's the Lie algebra for each I. This is important for us in representation theory because SL2 representation theory is very, very beautiful. But in order to go to any affine setup or whatever, it is some kind of a gluing process. So knowing the SL2 representation theory and interacting with different things, we actually develop the representation theory for the entire affine Lie algebra or semi-simple Lie algebra, whatever you tell. So this is important for us. We say that a linear functional alpha is a root if the corresponding root space G alpha which is defined this way, is non-zero. And the dimension of this root space is what is called the multiplicity of the root. And we will denote delta to be the set of all roots. There are many properties of that. I'm not going to that. But in particular, corresponding to the null vector A0, A1 up to AN that I told you, if we take this integral combination with those AIs of the alpha I, that gives us a root delta, which is called the null root. And this is the so-called imaginary root. Any non-zero multiple of this root in the affine Lie algebra case is also a root. Okay, but in general, multiples of roots are not roots. But in affine case, this is the special situation. And then remember that I told you that you have a left null space also spanned by B0, B1 up to Bn. If you take those Bi's and take the integral combination of H0 through H1, that becomes a central element of the Lie algebra. And we will call it the canonical central element. So the center is spanned by this element. Now, with these notations, the affine weight lattice again we will denote as P, and this can explicitly be written as the integral lattice with basis lambda 0 through lambda n and the null root delta. And we will denote P plus to be the set of dominant weights. So what dominance means is that on HI, it should be non-negative for each I. Now the elements of P are called affine weights and P plus are called affine dominant weights. Now, if I drop that delta, from P, that lattice, then I will denote the rest as P bar. And that's called the classical weights. Well, this has nothing to do with the finite dimensionality. Okay, it's just a name. We will call it classical weight. And similarly, the elements of P bar plus will be called classical dominant weights. The level of a weight is the number, the integer lambda c being the center, that will usually denote it by L. This is called the level of the weight. Okay, so now I have the algebra. Now let's look at the module. Now here there is some special situation, as you can expect. Now we are landing in infinite dimensional representations. This also, irreducibility extends to infinite dimensional vector spaces. So let's take V to be a G module and take mu to be any linear functional in on H. Denote V mu to be the set of vectors such that H dot V is mu H times V for all H in P check. We'll say that mu is a weight if V mu is non-zero. And the dimension of this weight space is what is called the multiplicity of mu, just like in root cases. We'll define a G module to be integrable if each of V is a direct sum of its weight spaces, and each weight space is finite dimensional. More importantly, V is a direct sum of finite dimensional GI modules for each I. We can decompose with respect to that SL2 copy, SL2 module. Now, for any dominant weight lambda, there is a unique integrable G module V lambda generated by the vector V lambda, that's the highest weight vector with highest weight lambda, as I already said. And indeed, V lambda can be expressed as UG dot V lambda, where UG denotes the universal enveloping algebra of G. Every Lie algebra has a universal enveloping algebra. Universal enveloping algebra is associative algebra, which is hence a Lie algebra under the commutator bracket. But this particular universal enveloping algebra, which I am not formally defining yet, vector space V is a G module if and only if it is a UG module and converts. That's important. And any highest weight module has weights of the form lambda minus integral combination of the simple roots. Now I want to go to the quantum case. So let's take a Q, just some indeterminate, particularly it should not be a root of unity. Now we will define Q integers, Q binomials, and Q factorials. Observe K subscript Q by definition is Q to the K minus Q to the minus K over Q minus Q inverse. And if you let Q go to 1, by formal L'Hopital's rule, you can see that this will be just 2K over 2. Okay, so it is K. Okay, so indeed, this is a Q integer. Okay. And with this notation, now we can define what we call a quantum affine algebra associated with a affine Lie algebra G. It is an associative algebra over K, which is a larger field now. You take F adjoining Q. This is rational functions in Q with coefficients in F. With unity, generated again by the same elements, EI, Fi, and Q to the HI, not Q to the H for each H. This is a formal exponent satisfying some conditions. Well, it is not so important to tell every condition here, but one important thing that I want to point out, so these conditions are explicitly written, you can look at the slide later, but one important thing is, if you let Q go to 1, then this quantum affine algebra UQG indeed go to UG. So in other words, all these relations, if you take the limit Q goes to 1, the resulting relations will be the relations for the universal enveloping algebra UG, which is a Hopf algebra. And so is UQG. They are Hopf algebras. We'll denote UQ prime G to be the subalgebra of UQG, just dropping the degree derivation D. So it is only generated by EI, Fi, and Ki plus minus 1, no D. And indeed, this UQ prime G can be regarded as a quantum group associated with the classical quantum data with P and P bar, P replaced by P bar. That's, oh, I missed pi check. But now, what is a crystal? I will focus mostly on the crystal for a highest weight module, V lambda, that I talked about. But this is a general definition. An affine crystal respectively a classical crystal, is just a set B together with maps, weight, EI tilde, FI tilde, epsilon I and phi, satisfying bunch of conditions like this. Well, these maps, EI tilde and FI tilde, are what is called the crystal operators or Kashiwara operators, referring to Kashiwara, who initially started it, as long as Lustig is not here. But anyways, both of them defined it, and there is a controversy who did it first. Anyway, so that's a different story. But these are called, now everybody is calling it Kashiwara operators. I don't know why, but anyway, so the important condition that I want to highlight here is Fi tilde B is B prime, if and only if B is EI tilde B prime. So, kind of these Kashiwara operators, as long as the vectors, the image is non-zero, they're kind of invertible. This does not happen with the Cheveley of generators. That's important. So these are kind of modified Cheveley generators. And indeed, this crystal B has a oriented colored graph structure where we take these elements in S as the set of vertices, and we draw a I arrow from B to B prime if Fi tilde B is equal to B prime. This particular, the beauty of a crystal is actually the action of Kashiwara operators on the tensor product of representation. And as you see, on a tensor of crystals, so each crystal corresponds to the crystal of a irreducible representation. For example, EI tilde, when it acts on a tensor product, there is no linear combination. It acts on either the first coordinate or the second coordinate. Okay. In general, when we look at the action of the Cheveley generators, EI and FI, you don't have this feature. Okay, so doing combinatorics becomes, with the representation, becomes much simpler. And here is, I gave you the example of a cell tree. We'll denote the crystal for V lambda by B lambda. So in particular, the as I already showed, V lambda 1 is a three-dimensional representation space. It is a highest weight representation. And we denote the crystal for it with just 3 nodes. And we label these 3 nodes as 1, 2, and 3, and indeed corresponds to epsilon 1, epsilon 2, and epsilon 3. Yeah. These are the so-called tableau description. And similarly, the lambda 2 is also a three-dimensional representation. And the highest weight lambda 2, remember, is epsilon 1 plus epsilon 2. So that's the highest weight is 1, 2, represented by 1, 2. And then first 2 acts, then 1 acts. And you produce these 3. Now, by the rule of tensor product, this is what I was trying to tell. It has a very nice combinatorial property in the sense, see, I put B lambda 1 up and B lambda 2 on the side. And then I have these 9 dots. These are the tensor products. And I draw the 1 arrow first. It is always left to right, top to bottom. So you see, I go left to right first. I always start from the leftmost. So I go left to right, but then there is a 2 arrow I cannot do anything. And this is a 2 arrow. I cannot do anything. So I come here, left to right, and then there is no. So once a place is occupied, I cannot do that. So like I cannot connect this to this dot. Okay. So I go down. But when I look at 2, you see I have the 2 arrow going from this point to this point, and then this point to this point. So I have this. This is just a very baby example of the situation, but this decomposes the tensor product of V lambda 1 and V lambda 2 to 2 irreducible modules. And the highest weights of the connected component, this connected component with 8 dimensions is this vector, which is the E1 tensor V1. And its weight is lambda 1 plus lambda 2. And this is just a one-dimensional representation, which is the highest weight is always 0. That's V0. So in particular, this decomposition gives us a 8-dimensional irreducible representation plus a one-dimensional representation. And the crystal graph for V lambda 1 plus lambda 2, just from this picture, following the notation how you put the tableau together, we get this crystal graph. And if these are what are called semi-standard tableaus of shape lambda. Lambda is capital lambda 1 plus lambda 2. That's I'm denoting as lambda. Okay, so its Young diagram is like this, 2, 1. And these are all the semi-standard tableaus you can have. And indeed, the crystal for any irreducible SLN module is described by the semi-standard tableau. Now I will define what is a crystal morphism. Well, so if we have 2 crystals, B1 and B2, we will say that they are isomorphic as crystals if there is a map C between B1 union 0 to B2 union 0, which is bijective and satisfies these 3 conditions. Mainly, you see it is weight preserving, and the epsilon I and pi of the image there, So incidentally, pi and epsilon I, really epsilon I is the number of high arrows coming in, and pi is the number of high arrows going out. And that is preserved both in the domain and the range. Okay, and this map commutes with the action of ei tilde and fi tilde. That's it. Okay, then we say that this is a crystal isomorphism. Well, actually, this crystal base was defined by Kashiwara and Lustig from different point of view. Yeah, around 1990. This is the precise date is different. So the immediate thing was to prove the existence of crystal base for a representation. And Kashiwara and Nakashima actually showed that these semi-standard tableaus do form a crystal base for the finite dimensional case AN, BN, CN, and DN. These are the simple matrix Lie algebras. And then actually then of course, we looked at the affine representation. Now, when we look at AN upper 1, we were able to give some description, explicit realization of the crystal base using what we called extended Young diagram. But soon we realized that when we go beyond A, particularly working with the symplectic case, which, for those of you who know anything, who know this area, the Cn upper 1 can be embedded as a sub-algebra of An upper 1 by just a simple folding. So, that's what we tried to see if we can get the combinatorics going, okay, but didn't work. And we found some very funny situations. So actually at that time, Miwa was here at NC State, and Kang was a postdoc with me. And we were working on this in Harrelson Hall. I still remember, this was 93. What is going wrong? And so we couldn't resolve it. And then, but we found interesting features. So when we returned to Kyoto, he talked to Kashiwara and explained what we found. And he, being such a brilliant mathematician, I have really very, very high regard for him. He saw what is going on, and that he noticed that indeed, in order for it to admit the crystal structure, the representation has to satisfy certain conditions. And this led us to the definition of so-called perfect crystals, to give realization of affine crystals. Okay, so, this is KMN square in 1991. It's two long papers. And so K square is, of course, Kang and Kashiwara. M square is Miwa and Misra. And N square is Nakashima and Nakayasuki. Okay, so actually, so Kang was working with me, and Nakashima was a PhD student of Kashiwara. Nakayasuki was a PhD student of Miwa. That's how it all got together. That's why it's an interesting situation. We were together in Kyoto for 2 months during summer, and that's when all these things happen. Okay, so we defined this so-called perfect crystal. It has 5 conditions. The first 2 conditions are representation theoretic, and the last 3 conditions are just combinatorial. Well, in particular, we have the concept of minimal element. Oh, I have only 10 minutes left, so I need to be a little quick. So the set of minimum elements gives you a way to define the highest weight vector for the representation. And the first thing, that this is what we had seen, before Miwa appeared on the scene, that if you take the C2 crystal, so C2 is SP4, the C2 crystal, the vector representation, that's a 4-dimensional representation, and that can be lifted to a affine representation by defining the 0 action sending V4 to V1. However, this level 0 affine representation is not a perfect representation. And the reason for that is that there is no uniqueness of B upper lambda 1 and B lower lambda 1. You see, there is B upper lambda 1 by definition, B upper lambda 1, epsilon B lambda should be lambda. Okay, it's the epsilon. So epsilon means the I arrow coming in. Okay, so one arrow coming in here to V2, but it is also coming to V4. No other arrows are coming in. So there is no unique way to define these two, and therefore we cannot satisfy the conditions. So this is not a perfect representation, but if we look at this finite dimensional, 5-dimensional representation corresponding to the second Dinkin node in C2, okay, that again can be lifted to a affine representation, and that does satisfy the conditions for a perfect crystal. But again, I need to point out that these perfect crystals are not unique. Meaning, you see, this C2 means C2 upper one has a 3 nodes, 0, 1, 2. So if you always, we start from a finite dimensional irreducible representation. So for each node, not including 0, there should be a perfect crystal. And indeed, we see that for the node 1, the level 1 perfect crystal is this one. So if we take the irreducible finite dimensional C2 representation, B2 lambda 1 plus B0, that's a 1-dimensional representation, and define the 0 arrow like this, then this is a perfect representation. So the perfect crystals are not unique. And indeed, these perfect crystals, we didn't know at the time, but later we found out these are actually certain finite dimensional crystals for certain finite dimensional G modules called KR modules. For this quantum affine algebra UQG, this was actually later proved. And they are parameterized by 2 parameters, K and L. L is the level, K is the Dinkin node. And then we, using this perfect crystal, we could prove the so-called path realization, which describes a affine crystal as tensor product of perfect crystals. Okay, so we showed in particular this isomorphism, and that led to a path realization. This path realization where this P lambda, as you can see, I have, okay, we defined what is called P lambda, P little lambda to be certain path, which we call the ground state path, and it has weight lambda. We know exactly, we of course know the formula for computing the weight of any path. And if we look at all lambda paths, they are isomorphic to the affine crystal P lambda. That was the theorem. Okay. In particular, for this B21 crystal that I showed you, the corresponding to lambda 1, the ground state path or the highest weight vector is just V3, V3. This is tensor product. Okay. And this is so semi-infinite tensor product. Okay, and the crystal for this affine module is indeed, this is just a partial diagram, and the actions are given by tensor product rule. This is the so-called signature rule, and that gives you these arrows, which Fi does act on it. And we, as I said, we have explicit formula to compute the weight of any path. So that was the I think, but now, well, after this was done, then we of course wondered So again, after this was done, Kashiwara was visiting me, and Kang was also here, and we started working on giving a path realization for the Verma module. And again, for those of you who know some things about this, Verma module as a vector space is isomorphic to the negative part of the quantum group. And Kashiwara had just proved the existence of crystal base for it. Okay. So of course, our natural question was, can we give a path realization? And that led us to the definition. So this is Kang, Kashiwara, and myself in '94. We introduced the notion of coherent family of perfect crystal whose projective limit we denoted by bk infinite. And that actually we used to give the path realization for the crystal for the Verma model. Okay. Here is some example, but anyway, I also had some geometric crystal in the abstract. So let me just say a few words. The geometric crystal was introduced by Bernstein and Kasdan for reductive algebraic groups, and Nakashima extended it to any Casimodi group, including the affine case. And in general, the geometric crystal, of course, the geometric object, it's a quadrupole. X is a variety, algebraic variety, and the EI are rational C star actions on X, and gamma I and epsilon I are rational functions satisfying certain conditions. I am not writing it. And it is said to be positive. This geometric crystal is said to be positive if it admits a positive structure. Roughly speaking, what that means, these are rational functions, so they are ratio of polynomials. And basically, those polynomials must have positive coefficients. Roughly speaking, that's what it means. Okay, so, and one important observation in that theory was that a ultra discretization, it's kind of a linearization, okay, where the product is mapped. So multiplication is mapped to addition. Division is mapped to subtraction. And addition is mapped to maximum. Okay, with this, a positive geometric crystal with this maps to a Kashiwara crystal. Okay, that was the important thing that Bernstein and Kasdan proved. And then around 2008, Kashiwara, Nakashima, and Okado conjectured that this Kashiwara crystal is isomorphic to a B infinite crystal of the Lang-Lang dual. That was the conjecture. And they showed only for vector representation, meaning the Dinkin node 1, the simplest case. And well, so then, I got fascinated with this work, and I started working on it around 2010. And the first, well, actually 2009, I was in Tokyo, and I was talking to Nakashima on this, and we did something before, but then we started working on this to prove the conjecture for k equal to 2, an upper 1. Well, now we were able to do that. And then the natural question is how to do for arbitrary k. And it, as you can see, it took us more than 5 years to actually prove the arbitrary, for arbitrary k, that's because the combinatorics becomes so complex that you don't know how to prove. So we actually developed something called lattice path combinatorics on a k by k prime rectangle. And we hope that some combinatorics people will actually use it for other things. But that actually helped us to do this proof. And I was hoping that I will talk about that a little bit, but time is short. And just to, so I will probably end it here, that in actually Sujata Prasad was one of my PhD students. So I gave her the problem to prove the conjecture for D5 upper 1. And at that time, one of Nakashima's students was a postdoc with me. And we worked on that project, and we were able to prove for prove the conjecture for D5 upper 1 at k equal to 5 Dinkin node. And this is actually the first time that this is the k equal to 5 has a significance. It is not the usual module, it is the so-called spin representation. And this is the first non-vector representation for which we proved the conjecture. That was the important thing. But then I talked to Sujata. She was, of course, looking for thesis project. So I said, naturally, let's look at D6 upper 1. And we found that there are significant differences between D5 and D6. And so it was worth working on that. And we saw that it is much more complex. But that actually became her PhD thesis. And we recently published that paper finally. It was in 2 papers. First one is giving the geometric crystal, which was basically in our thesis. And the second one was the proof of the conjecture. And currently, Nakashima has joined us, and 3 of us are trying to find a general proof for arbitrary n, arbitrary rank n. Okay, so there are a lot of problems. I think this probably is a good time to stop. I should also, I think, is Erika here? Yeah, Erika is actually working on proving this conjecture for Cn upper 1.